I'm going to explain the disk method for calculating volumes of rotation, and I'm going to do it really slowly over a couple of videos, so bear with me. So typically the problem is that you're given a region, you're given an axis of rotation, you rotate the region around the axis, and you have to calculate a volume. So let me pick a region. Here's my region. So its boundaries are defined by the curve y equal to x square for x, let's say less than 1 and greater than 0. So less than or equal to 1, greater than or equal to 0, by x equal to minus 1 and by y equal to 1. And my axis of rotation is also x equal to minus 1. Oh, I guess I should add x equal to 0 as well. Okay, let's see what the region looks like. So here's the y-axis, here's the x-axis. This is x equal to 1. I would say here is x equal to minus 1. This is y equal to 1. This is the graph of that piece. So this is y equal to x squared, x going from 0 to 1. And then the second boundary is the boundary x equal to minus 1. The third boundary is the boundary y equal to 1. And the last boundary, oh, this should be y equal to 0. Sorry, the last boundary is the boundary y equal to 0. Okay, so the region we are interested in is from here all the way out to here, down to here, back and back up here. So that's the region we are going to rotate. The axis of rotation, which I'm going to draw in red, is also x equal to minus 1. So this is the axis of rotation, and so now I have to rotate this entire region around this axis. So this point rotates around here to go all the way out here. This point rotates around here to go maybe here. So that's the bowl-shaped region whose volume we're interested in. So the method of disks works this way. We create a new variable and we'll call that variable s, and the variable goes along the axis of rotation. So here, for example, is one particular value of s. Now what we're going to do is we're going to slice through the volume with a plane perpendicular to the axis of rotation at the height s above the x-axis. So let me try to draw that plane. And this height is s. I'm not going to draw my plane all the way through because the diagram will get really messy if I do that. But you should imagine this plane cutting through the volume at the height s. So when you do that, you get a cross section of the volume, which of course ends up being a circle. Now we're going to increase our s slightly, and so we get a second plane, and that height we're going to take as s plus ds. So we're going to differentially increase s. That's an infinitesimal increase in the height of s. So of course that thickness is just ds. And then when we take the second slice and slice through this, we get a new circle right on the top of the first circle. And as a first shot at solving the problem of calculating volumes, we're just going to try to calculate the volume in between these two slices. So to to make my life a little bit easier, let me just draw those two slices so we can look at them a little bit more carefully. So here's the top slice. Here's the bottom slice, and that's the volume that we're interested in calculating. That thickness is ds. And strictly speaking, ds is an infinitesimally small thickness. So when this thickness is infinitesimally small, the top circle and the bottom circle have pretty much the same radius. And let's call that radius r. So here's the radius r. And so this entire thin section that we pulled out of this volume is a disk for ds being very small. And of course, the disk is just another name for a cylinder. That's the axis of the cylinder. Ds is the height of that cylinder. And now we can calculate the volume of that tiny cylinder. The volume is just the area of this face, which is pi r squared, times the height of the disk or the thickness of the disk, which is ds. And that's going to be the infinitesimal volume of just that part in between the two slices. Okay, now what we're going to do is we're going to imagine that we move s from this value, its smallest possible value, to this value, its largest possible value. And for every value of s, we're going to calculate this infinitesimal volume dv, and then we're going to add up all of these dv's. And when we add them up, we'll have the volume, the entire volume of rotation of that figure. Now, adding up infinitesimal volumes, of course, is the same thing as integrating. So v, the entire volume, is going to be the integral from some limits a to b pi r squared ds. Now, exactly what are these limits? Keep in mind your variable of integration is s. So these limits are the smallest and the largest value of s that define our figure. So if you go back to the original figure, the smallest value of s is the same as the smallest value of y that defines this figure, and that's 0. The largest value of s is the same as the largest value of y that defines this figure, which is 1. So for this particular case, for this example, a equals 0, b equals 1. There's one other subtle point you have to know, which is that r, although I haven't written it explicitly in this formula, r is a function of s. And what I mean by that is, if you go to the original figure, as s changes from down here to up here, the r, the radius of the disk, changes from this value continuously up to that value. And the trick to using this formula for calculating the volume is to figure out how r is a function of s, to write down an explicit formula for r as a function of s. Once you have that formula, you just plug it into this equation, you do the integral, and you have the volume. So in the next video, I'm going to show you how you get r as a function of s. And by the way, it should be really clear to you now why we call this the method of disks, or the disk method. Really what you're doing is you're taking the volume and you're approximating it as a sum of volumes of disks. And in the limit, as the thickness or the thinness of that disk goes to 0, that approximation is exact and you get the volume of rotation.